Hi all, today we'll be talking about a Leetcode problem, cheapest flights within K stops. Let us go through the problem statement first. There are n cities connected by m flights. Each flight starts from city U and arrives at city V with a price W. Now given all the cities and flights together with starting city source and destination city dest, your task is to find the cheapest flight from source to destination with up to k stops. If there is no such route, output -1. Let us go through the sample. It says that the number of nodes are 3, that is, there are 3 cities, and the edges are given. So 0 to 1 has a cost of 500, and 1 to 2 has a cost of 100, and 0 to 2 has a cost of 500. The source city is 0 and the destination city is 2, and the number of stopovers allowed is 1. So basically what this question is trying to ask is that we have to go from any source city to a destination city given the number of stopover limits k. That is, we could either take a direct flight from source to destination city, or if stopovers are allowed, we can take a stopover and go to the destination city. Our objective here is only to minimize the cost of our entire travel. That is, if I travel from 0 to 2 in this node via direct flight, it will cost me 500. However, if I take a stopover, which is within our stopover limit k equals to 1, then I can travel from 0 to 2 in only 200, which is much lesser than 500. So basically our objective is to minimize this cost of our travel given that the stopovers are within our stopover limit. Similarly, if we go to the second sample here, we again need to go from 0 to 2. However, there are no stopovers allowed. So if there are no stopovers allowed, we have to take the direct flight from the source to destination city, and it will cost us 500. So basically the problem is to find the minimum cost with the constraints of stopover. Whenever we want to find the shortest path between any source and destination, we think in terms of breadth first search or Dijkstra's algorithm. Breadth first search works well when there are no weights associated with the edges. However, we see that there are weights associated with edges here. 0 to 1 is 100 and 100 and 500. So like edges have weights, so we'll try to think in terms of Dijkstra's algorithm here. Also, in Dijkstra's algorithms, we utilize the concept of min heap. We'll try to use min heap here because we want to minimize the cost. We want to take out the minimum cost. Whenever we are at a certain node, we want to take the node with minimum cost from, we want to take the edge with minimum cost from the current node. And if it is within the stopover limit, we'll go ahead and push this into our min heap. And if it is exceeding the stopover limit, we'll simply not explore this path any further because we can't take more than k stopovers. So basically we'll try to build our graph first. So let us keep a map of int and vector of pair int int. The key of this map would be the source city, like given an edge like 0, 1 and like this edge 0 to 1 has a cost of 100. So 0 will be the source city here and 1 will be the destination city here, or U or V we can say. 0 will be U and 1 will be V and the cost will be 100. So that's what it denotes. The first is U, the first element of pair is V, and the second element of pair is the cost, which is weight of the graph, weight of the edge of the graph. So we'll try to build this graph. I is less than flights that size, I plus plus. Int U is flights i's first element. Int V is flights i's second element, and the cost is flights i's third element. So in our map In U, we'll push V and the cost. We are keeping a vector here because from a given node there can be multiple edges. So to account for the multiple edges, we are keeping a vector of such pairs. So we have basically built our adjacency list here. Now we need to start the Dijkstra's algorithm. We'll be needing three parameters here. The first parameter will be the weight, that is the weight of that is the cost that is the cost, yeah, the weight, the cost. And the second parameter will be the node itself, and the third parameter in our priority queue will be the number of stops k. And whenever our k exceeds the stopover limit, then we'll not explore that path any further. So let me define a priority queue here, which is basically a min heap. As we talked about, there will be three elements in this uh, pair. Like we'll keep a pair of like pair of int, int. So the first int denotes the cost of traveling till here. The second int denotes the node which we are at currently, and the third int denotes the number of stopovers we have taken till now. So it is the current cost, current node, and current stopover count. And we'll make a min heap out of it. Let me copy this. Priority queue PQ, or priority queue is made. We'll start with the source node. So in our priority queue, we'll be pushing. Initially, the current cost will be 0 because we are starting from the source node. The current node will be the source node, and the current number of stopovers will be 0 because we haven't taken any stopovers till now. While our priority queue or min heap is not empty, we'll continue doing this. Int U will be the current node. The current node is in priority queue stop dot second dot first. Int C, which is the cost, will be current cost will be priority queue stop dot first. We have kept it as the first parameter because we want the priority queue who sorted on the basis of minimum cost of the edges. And then we'll have the current k, which is priority queue dot top dot second. So basically here, if the current node which we are at, which is kept in U, is the destination node, we simply need to return the current cost which is stored in C here. Or if the current number of stopovers that we have taken till now is already greater than the number of maximum stopovers that we are allowed, we'll not explore this path any further and we'll simply continue from this. We'll not push any other nodes in this priority queue right now because we have already taken the maximum number of stopovers that we could take. Otherwise, we'll iterate over our adjacency list. I is less than or maps current node's children I plus plus. Now we'll push into our priority queue the edges connected to the source node. So we'll be pushing make pair of the source in the weight first. So the current cost will become the cost till now plus the weight of the edge between the two nodes here. So the weight of the edge is stored in our map in the, like the cost was the second element of the pair, so it will be second. So this is the cost of this edge between uh, the node u and v. Let us denote int v as np u I dot first. This is the node and this is the cost of the edge. So we'll push the current cost into our priority queue, and then we'll be pushing the current node, which will be v, and the number of stopovers that we have taken till now, which will be the current stopover plus 1. So while doing this, whenever we reach the destination, it is guaranteed that will be the minimum cost till now, because that's the way Dijkstra's algorithm works. We have kept a priority queue, which is a min heap, and it is keeping the minimum cost thing, which is keeping track of the minimum cost, and the number of stopovers are getting tracked here. If a stopover is ever exceeding, then we cannot explore that path any further, and that's how our number of stopover limit is also getting tracked. Now finally, we'll return -1 if we find no answer, as it says if there is no such route, output -1. Otherwise, we'll always reach the destination and we'll return this cost. We'll just try to compile this. I missed a bracket, so pair int 1 2 3 1 2 3 1 2. Okay, this was fine. 1 2 3 1 2 3, and the one for priority queue. Okay, we have not popped the element from our priority queue. When we are done traversing the current node, we need to pop it out of the priority queue, otherwise it would go into diagrammatic exceed. Yeah, looks good. We'll check on both the samples. Looks good. Let us try and submit this. It is accepted. Thank you so much for watching.